Welcome to the optional lectures on Kepler's laws. I think deriving those is one of the really cool applications that we have of vector calculus. Need to make a couple of preliminary remarks though. First of all, these videos are not based on the argument that's presented in your current textbook, the one by Stewart. Stewart does make an argument to prove Kepler's laws. It's a great argument. It's just different from the one I'm going to present here. So if you're going to your textbook to try to understand these videos more, it's probably just going to cause more confusion. And that's because it's a different argument for the same result. I'm basing this on the argument that's in the previous textbook that we used to use for this class. That's the book by Anton, Bivens, and Davis. So I want to be clear about that for two reasons. One, so that you don't use Stewart's textbook to try to clarify this argument, which is not the one in the book. But two, I want to make sure I give credit to those authors because I did not come up with this. Another thing to say. You will find that I am using my notes quite a lot as we work through this. And you may find that there are times when you're saying, why is she writing that down? Your job is not, even though I usually love to understand why, your job is not to understand why I'm choosing to write down this particular thing, but why I can, why it's true, okay? I'm going to write down a bunch of stuff and it's going to turn out to be useful. Whoever came up with this argument first, and I say whoever it was because I don't know what argument Kepler used to come up with his result, and there's more than one way of proving his result, and so I don't know that he came up with this particular argument even though he did come up with the result. Okay, whoever came up with this first probably wrote down a whole bunch more stuff than we're going to write down today. Because very often when you're trying to figure out, to solve a complicated problem, you write down a bunch of stuff that's true and most of it is irrelevant and not useful. You spend more time getting false starts and going down paths that lead nowhere than you do following the path that leads you to your answer. Okay? Well, I'm not going to spend that time because I'm not the first one coming up with this. I'm presenting what other people have done that led to the answer. Okay, but realistically, if you were to try to sit down and say, let's figure out Kepler's laws based on what we know from vector calculus, you'd probably have lots and lots of false starts. You'd write down all sorts of things that would be true, but just not relevant to the problem. And we're just skipping those steps. Okay, let's see. I've written down some notation here that we're going to use. So and as we talk through this, I'm going to also talk a little bit about some simplifying assumptions that we make. Now, anytime you're trying to model a real-world situation, we do make some simplifying assumptions. It's possible to simplify a problem so much that the problem you end up solving has nothing to do with the real-world problem that you were trying to describe. What you need to do when you're trying to describe something out there in the physical world is you do make simplifying assumptions so that you've got something to work with in the math. You come up with a model, and then you just have to compare that model to reality. Now, we're going to show that the planets orbit the sun in an elliptic path. That seems reasonable based on reality. We have these things called seasons, okay? So the observational data that we have is consistent with the model that we can come up with. So that tells us that the simplifying assumptions that we made probably weren't too far off base. That's not guaranteed to happen. That's an important step when you're trying to model something in the real world, that you make some simplifying assumptions, but then once you've got a model based on those assumptions, you compare it to reality to see if it's actually doing a good job. Okay, so we're going to let m represent the mass of the sun. Little m will represent the mass of a planet. F is going to be the force of gravity that the sun exerts on the planet. And one simplifying assumption that we're going to make is we're going to suppose that this is the only force acting on the planet. Now, I actually know that's false, right? The moon exerts a gravitational force on the Earth. So the sun is not the only thing that's affecting the Earth. But what we're hoping is that the force of gravity that the sun exerts is so much bigger than all these other forces that we know are out there that those other forces are negligible. Okay. And it turns out that that is an assumption we can get away with. G is just going to be a gravitational constant, so we're going to use that a little bit later on in describing what that force vector is. We're using r of t for position, And I'm going to use the physics convention that if I write the name of a vector without the bar over it, I'm using that to denote the magnitude of that vector. So if r of t is the position, what we're going to do is we're going to put the sun at the origin. We're going to introduce a coordinate system with the origin being at the location of the sun. And then r of t would be pointing from the sun to the planet. Okay? And so r, the magnitude of that position vector, would just be the distance of the planet from the sun. The vector v is our velocity vector. V without a bar over it is the magnitude of velocity. That would be our speed. Okay. And for both of these, if we put a little subscript of 0, that's going to mean our initial position in this case and our initial velocity in this case. So r subscript of 0 is the same thing as r evaluated at time 0. That's my initial position. V0 is my velocity at time 0. Now, we are also going to make the simplifying assumption that neither of these is 0. I think assuming that the initial position is not 0 is very safe. If the initial position was 0, we would be at the center of the sun. We would not be doing any math. Okay. But we are going to suppose that we're moving. We're not starting at a time when we're just standing still in space. The initial velocity is going to be 0. Okay. And then I'm using a of t to represent the acceleration. Okay, now we're going to make another simplifying assumption, and that's going to be that r, the distance from the planet to the sun, is at a minimum when t is equal to 0. Now, of course, we'll choose what time is time 0, what time is our starting time, by waiting until r is at a minimum. But we are going to make the assumption that there is some minimum distance. Okay. Now let's talk about whether that seems reasonable or whether that's too much of an assumption to be making. Well, even if we had a circular path, now we know the result, we know we don't, but if I did have a circular path, this would still be true. Because if I had a circular path, this distance would be constant, and anytime I have a constant function, it's always at a minimum value, which is exactly the same as the maximum value that it's always at. Okay, so this doesn't rule out having a constant distance. Okay, it does seem reasonable based on the fact that we have seasons, so that there's a time of year when we seem to be maybe closer to the sun because things are warmer, and a time of year when we seem to be further away from the sun because things are colder. So it does seem reasonable based on observational data. It does rule out the possibility that we're continually spiraling in towards the sun and just sort of gradually getting closer and closer and closer. Okay, so we are ruling out some possibilities by making this simplifying assumption. Okay, it's going to be useful for us for a couple of reasons, one of which we'll see right now and one of which we won't see till the end of this argument. But we're going to make that simplifying assumption. This is something that you might feel skeptical about. Great. That just says, okay, we're going to have to, once we get our results, see, do our results match reality well or not? And of course, we know ahead of time that they do because we're not deriving this for the first time. We're just following the steps of people who derived this before us. Okay. Now, a consequence of that is that the initial position and the initial velocity are going to be perpendicular to each other. Okay. I'm going to leave it to you to convince yourself that that's true. The book actually stated that as a separate assumption, that the initial position is going to be perpendicular to the initial velocity, but that really does go along with this right here. Now, what that's going to allow us to do is set up a coordinate system. So I already said we were going to put the sun at the center, or at the origin, rather. So we're going to put the sun at the origin. I'm going to choose to put my initial position on the positive x-axis. So if I do that, let me get a different color marker here. There's my r naught, my initial position, and I can just say that's r naught times I. Okay. So r naught would be my initial distance, and I've put it on the positive x-axis, so it's that positive multiple of I. Okay. Now, I know that this direction is going to be a direction that's perpendicular to this direction. I'm just going to choose that to be the direction of my positive y-axis. Now keep in mind, the x, y, and z axis aren't pre-existing. They're not floating out there somewhere in 3 space. What I'm doing is I'm saying, oh, I've got this vector r naught, and I've got this vector v naught, which I know is perpendicular to it. I am going to introduce my axes so that that's the x-axis and that's the y-axis. So we're introducing the axes based on where these things are. So this would give me my v naught, which would be the initial speed times j. Okay. All right, excellent. And I'm going to just introduce another vector. If I took r naught crossed with v naught, if I cross these two things, I can tell just from the right-hand rule that's going to give me something that points straight up. I'm going to just call that b. And I can see that's going to be some positive multiple of k. I don't know how long it is. I could actually calculate how long it is. That's actually just going to be r naught v naught times k. The initial position distance times the initial speed times k. Because I'm crossing this vector and this vector, so I can factor those scalars out, and then I cross j just gives me k. Okay, excellent. So, if our conclusion is going to be that we travel in an elliptic path, seems like that's making a huge assumption, because an elliptic path would lie in a plane. We're in 3 space. There's nothing that says the path of the planet has to lie in a plane. Maybe the path is like so. That doesn't lie in any sort of a plane. Why isn't that possible? Well, we're going to actually prove that with these initial assumptions, our path will lie in a plane. In fact, it's going to lie in what we've created as our xy plane, and that's going to make the problem a lot easier to work with. So that's where we'll pick up in the next video.